Greetings, this video is for Calc 2, section 11.6. Section 11.6 deals with absolute convergence and the ratio test and root test. In this video, we're going to take a look at what's happening with the ratio test. So remember that a series is the summation of an a sub n from n equals 1 to infinity. And so that's equal to an A1 plus an A2 plus an A3 plus an A4. So a ratio test then says there are three sort of things we're looking for in a ratio test. What we do in the ratio test is take the limit as n approaches infinity of a sub n plus 1 divided by a sub n, take its absolute value. If that limit is less than 1, then a sub n, the series, is absolutely convergent. And remember, if the series is absolutely convergent, that also means that a sub n itself is convergent. If we find that the limit as n approaches infinity of a sub n plus 1 divided by a sub n after we take the absolute value, this limit, if that's equal to L and L is bigger than 1, or that limit is equal to infinity, then a sub n is divergent. So that's the case where a sub n is divergent. And finally, in the third case, if we find that that limit equal to 1, we know nothing from this test. And to be honest with you, it can be kind of frustrating because we do all this work, it's equal to 1, and we don't know anything, we have to do something else. So for example, determine if the summation from n equals 1 to infinity of minus 2 raised to the n divided by n squared is converging or divergent. So now we're in the ratio test section, so I'm going to do a ratio test. But usually if I wasn't in the ratio test section, if I didn't know what test I should use, my first go-to is always the ratio test. That's the one I like the best. And if that one works, then great. If not, then I have to look for something else. So the ratio test says that I'm going to take the limit as n approaches infinity of a sub n plus 1 divided by a sub n, take its absolute value. I want to point something else out here, that's also equivalent to the limit as n approaches infinity of the absolute value of a sub n plus 1, that multiplied by a sub n raised to the minus 1. Those are mathematically equivalent things. And I point that out because often my a sub n plus 1 and my a sub n are fractions themselves. So I have a fraction divided by a fraction. So if I write that fraction divided by a fraction as the fraction multiplied by the reciprocal of the bottom, that's often a good step to help out my algebra. So a sub n plus 1 is minus 2 raised to the n plus 1 divided by n plus 1 n squared. And then a sub n is equal to minus 2 raised to the n over n squared. So now I have to find the limit as n approaches infinity of a sub n plus 1 divided by a sub n, take its absolute value, and that's equal to the limit as n approaches infinity of minus 2 raised to the n plus 1 divided by n plus 1 and square it, multiplied by the reciprocal of a sub n. And the reciprocal of a sub n is n squared divided by minus 2 raised to the n. And all of that, of course, is inside the absolute value. So then that is equal to the limit as n approaches infinity. And I'm going to line up minus 2 to the n plus 1 divided by minus 2 to the n. All of that multiplied by n squared divided by n plus 1. That quantity squared. Still inside the absolute value. So I took these two terms and wrote them as a common fraction together, and these two terms and wrote them together as one fraction. And I did that because everything is being multiplied inside the absolute value. So then I have the limit as n approaches infinity, and this first fraction can simplify to minus 2 raised to the first. And then I'm going to multiply that by n squared over n plus 1 quantity squared inside the absolute value. So then this is equal to the limit as n approaches infinity of minus 2, take the absolute value, multiplied by the absolute value of n squared over n plus 1 quantity squared, take the absolute value. The absolute value of minus 2 is positive 2, so I can pull that outside the limit, so I have 2 times the limit as n approaches infinity of n squared over n plus 1 quantity squared inside the absolute value symbol. Once again, what I did was said, well, this is a positive thing. Absolute value of negative 2 is always positive. It's a constant, so I pulled the constant outside the limit. Now I'm dealing with things inside the absolute value that as n approaches infinity are always going to be positive. I have something positive squared, that's always positive. I have something that I'm going to add a constant to and square it, that's always positive. So I'm going to have 2 times the limit as n approaches infinity of n squared over n plus 1 quantity squared. And I'm not writing the absolute values anymore. This series is always going to be positive. Okay, so now I have to apply the limit. So I have the limit as n approaches infinity, and I'm going to multiply both top and bottom by 1 over n squared. So I have n plus 1 squared over 1 over n squared. And when I do that, I get 2 times the limit as n approaches infinity of 1 over n plus 1 squared divided by n squared. And that is 2 times the limit as n approaches infinity of 1 over n plus 1 over n, that quantity squared, which is 2 times the limit as n approaches infinity of 1 over 1 plus 1 over n, that whole thing squared. And when I apply that limit, I get 2 times 1, which is equal, of course, to 2. And 2 is bigger than 1. And from my 3 cases of the ratio test, if the limit is bigger than 1, then the series is divergent. So from that, I'm going to make the conclusion that n equals 1 to infinity of minus 2 raised to the n over n squared is divergent. And I did that because after applying the ratio test, I got 2, which is bigger than 1. And if I'm in the case where I'm in case number 2, so the limit is bigger than 1, so we say it's divergent. Okay, let's look at one more example. Determine if the series n equals 1 to infinity of n times e to the minus n, if that converges or diverges. So again, I'm going to use the ratio test. And the ratio test, my a sub n plus 1 is equal to n plus 1 times e to the minus n plus 1. And my a sub n is equal to n times e to the minus n. So I need to find the limit as n approaches infinity absolute value of a sub n plus 1 divided by a sub n. That's equal to the limit as n approaches infinity. Absolute value of n plus 1 times e raised to the minus n plus 1, all divided by n times e to the minus n. That simplifies to the limit as n approaches infinity, absolute value of n plus 1 e to the minus 1, all divided by n. So what I did is take this e to the minus n plus 1 and distributed that. So e to the minus n plus 1 is equal to e to the minus n minus 1. And then the e to the minus, that's being divided by e to the minus n. So e to the minus n. And when I simplify that by putting e to the minus n into the top, that becomes e to the plus n. So that all simplifies to e to the minus 1. Okay, so then all I need to do is rewrite this as the limit as n approaches infinity, the absolute value of e to the minus 1 times the absolute value of n plus 1 over n. I get e to the minus 1, take its absolute value, is always going to be positive. So that's 1 over e times the limit as n approaches infinity, absolute value of n plus 1 over n. And once again, n plus 1 over n, as n approaches infinity, those are going to be positive things. So I can write this as 1 over e times the limit as n approaches infinity of n plus 1 over n. And that is equal to 1 over e times the limit as n approaches infinity of 1 plus 1 over n. And that's equal to 1 over e times 1. And 1 over e times 1 is the same as 1 over e. And that is certainly less than 1. It's less than 1. So from my test, if I have condition number 1, then where my limit is less than 1, then it is absolutely convergent. So something that is absolutely convergent is convergent.